thickness becomes the average stress. So, in-plane behavior. In fact, in composites, we will separate the in-plane from the out-of-plane, and then we'll talk about coupling, where the two are combined. So, in the case where we only have in-plane loads, and we also assume that there is no bending, this means that there is that the layup is symmetric. We will define that later on. Don't worry about what that means. What I need you to keep in mind is we have an applied load which only causes in-plane deformations. So this means that the strains anywhere through the thickness are constant and equal to their values at the mid-plane. And traditionally we put a 0 or a naught to denote the mid-plane strains. So mid-plane strains, epsilon 1, epsilon 2, and gamma 1, 2. Now if I take that relationship from before, which was, 1, 2, 1, 1. I take this, which is the general expression of stress-strain equations. I integrate that with respect to z. So if I take the first one, I had sigma 1, 1 was q11 epsilon x0 plus q12 epsilon y0 plus q16 gamma xy0. So I just integrate everything with respect to z. I know by the definition we just introduced that the left-hand side is my nx, the force per unit width. And then, because I said this is all in plane, and this is a constant strain, epsilon x0, epsilon y0, and gamma xy0 with respect to z, I can take those strains outside the integrals. As soon as I do that, I end up with these interesting quantities, integrals of the stiffnesses through the thickness, integral of stiffness q11, q12, or q16. And these are now called by everybody A11, A12, and A16, which means if I take my stress-strain relationships and I integrate through the thickness, I arrive at my basic plate relationships, which relate the forces per unit width to the strains through this A matrix. I just showed you how A11, A12, and A16 come about. So in general, Aij, where I and j can be 1, 2, or 6, are given by this integral through the thickness. Because within each ply, however, the corresponding Qij is constant. So each ply has its own Qij, Q11 or Q16 or whatever it is. So I can simplify these integrals as summations over all plies. Basically, within each ply, I only get the Qij of the kth ply. And the integral with respect to z would give me a zk minus 1. Basically, this is my z-axis now. And I call this z0. This is z1, z2, and so on. So if I am doing my integral of dz from the bottom layer to the top layer would be, let's say, z2 minus z1 in this case. So in general, it would be the z coordinate of the top layer of the top location of a ply minus the corresponding one for the bottom, and that multiplied by the corresponding Qij. If I take that and add it up across all the plies, I get the corresponding term in the A matrix. And your homework 1 has a lot to do about the A and the D matrix, and you guys will have to either write a program. I strongly recommend to do this, or use the packages that we have available. Are there any questions? I'm done for today. Oh, okay with you? Okay, all right. All right, I will see those of you left on Friday. And we have a bigger room on Friday, but hopefully next week maybe they can give us another room. We'll see what happens. And if anybody has that paper with a sign-up sheet, please, if I can bring it over.